Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And also Professor Ahuja at UIUC. So there are various projects I'm going to talk about. 2D texture synthesis, I guess everybody is familiar with that. 3D texture, the name of 3D texture is kind of confusing. So in graphics, there's this concept, volume texture, which means you associate the texture with all the points in a 3D volume. But 3D texture is actually different from that. It basically refers to surface details. So on the surface, you have geometric details like bumps, dents, like this carpets. So 3D texture, we refer to this kind of surface geometric details instead of volume texture. So I'll talk about a technique to reconstruct this kind of geometric details from shadow information, shadow and shading information. But so for 3D textures, there are basically two different representations. The first, we actually explicitly represent the geometric details and also the reflectance. So that's called 3D texture. But also, we can use image-based rendering modeling technique that represent the 3D texture using a bunch of images from, taken from different camera positions, lighting conditions. So that's called bidirectional texture function. But the bidirectional texture function, needs a large number of images to capture the whole appearance, the collective appearance of the texture. So typically, some data compression scheme needs to be employed. So I'll talk about some new tensor-based compression scheme for this kind of bidirectional textures. And last, I'll briefly talk about surface texture by generalizing the Poisson equation. If we have multiple sources, how can we synthesize texture using these multiple input textures and merge them together onto some surface? And also, we can also perform fluid simulation on surfaces. Again, we can also use the Poisson equation to do that. So this is a recap of last year's SIGGRAPH paper. So for 2D texture, a problem is that for structure texture, so typically there are two types of textures. One is highly random textures, like the details are very small so that you really don't care about the structures in that. But another type is that the texture have very strong structural information there. So you can see clearly the individual objects in the texture, like in the first example, the eggs, or in the stone. You can see the individual pieces of object. But if we don't care about the contours and boundaries of these objects, then the synthesized results is going to mess up the boundaries and end up with incomplete objects, like this kind of thing. So you have contours sticking out in the middle of some object. That doesn't really make sense. So we focused on this problem and tried to figure out why this could happen. The reason is that in texture synthesis, typically people use template matching, like SSD type of error metric to search the neighborhood patches. So, and this kind of error metric actually can miss this kind of thin details, thin structural details, because it's a point-wise comparison. So, for example, if we have a signal, 1D signal like this, and if we shift the signal to somewhere, even though they're exactly the same, if you compare point-wise, you get a large error. That's the kind of error you can get from SSD. But if you consider the geometric distortion, say if you look for this point, you look at the surrounding neighborhood of that point and see whether there's some similar pixel with similar color in that neighborhood, then you can get a more accurate matching error there by considering both the color differences and also the geometric distortion. So for example, this is a periodic texture. If we apply texture synthesis to it, we can get perfect result like this. But if we slightly warp the texture, okay, then SSD would miss this kind of distortion and give results like this that has a lot of discontinuities there. So we decided to explicitly consider this kind of features. The motivation is that we can introduce some sort of deformation, but try to avoid discontinuity. Because humans are very sensitive to the kind of contours, boundaries, this kind of high-level features, but tolerant to small deformation. So this is a small deformation, warping, as I shown before in the previous slide. We can hardly observe the distortion there, actually. But if there's discontinuity there, we can see them. But for texture synthesis, we need something robust. So we can't detect all possible features like in computer vision. So we focus on some easy-to-detect features like edges and ridges, because there are filters to detect these kind of features very easily. So as a result, we introduced some technique that combine both color and geometric feature information. So the algorithm takes, so this is the input texture. We first run analysis on it, texture to extract this feature map. Then consider both as the input of the synthesis algorithm. And during the synthesis, we consider both color matching. So color matching is still using SSD. But for the geometric features, we use Hausdorff distance. Actually, in addition to Hausdorff distance, we also consider a tangent. So at every feature pixel, we also estimate some tangent direction. Consider both position and a tangent direction, the differences in both things. And when we search for a neighborhood. So as a result, we can synthesize a new texture, also a new feature map as a byproduct. So that's the kind of result we want. So you can see the Eric's less broken than from the previous result. And so to combine this thing, we simply just have some weighted average of the two error matches together. To perform this kind of feature detection, there are a few simple steps. First, we run this bilateral filtering to basically enhance the image. So the bilateral filtering removes noise, but still preserve features. Then after that, because the noise has been removed, we can simply apply finite differences, like gradient estimator or Laplacian estimator, to estimate edges. So the gradient is for edge, and Laplacian is for ridge. We don't need any Gaussian filter like this kind of thing, because the bilateral filtering already performed this smoothing and cleanup step. And then after that, we can simply do some by thresholding, like in the Canny detector. So use a high threshold to detect the major features, but they are broken. We need more continuous features. So in the second pass, use a lower threshold. But this lower threshold is a spatially varying lower threshold. It looks in the neighborhood of strong features. See what kind of filter response those strong features have. Then lower the threshold by a fixed ratio to detect lower features. So that's why we can get some nice thin features like this. So here are two examples. The input texture can involve both very regular textures or stochastic features. So notice that in this texture, the feature is actually not very continuous. They are still broken, but we can get very nice results from that. So continuity is not a requirement, but it would be nice to have more continuity in the future. So here's a comparison with previous synthesis results with graph cut, quilting, and a textile mask. So you can see so our technique. So these are three very difficult textures. For easier textures, the difference is not going to be so obvious. But these are difficult structural textures. So in our technique can produce almost perfect results. And you can see previous technique actually can produce a lot of discontinuities. especially for this stone texture. Because it's a geometric feature map, we can actually create new shapes like this. So you can see this stone actually is not present in the original texture. It's assembled from partial contours to generate this new shape. So that's 2D texture. And in real world, we have a lot of 3D textures. You can see these are a few examples from the Curie database at Columbia University. So you can see this is probably a concrete surface. This is a sponge. This is aluminum foil. This is some leaves, simply multiple layers of leaves. So in 3D texture, you have all these effects like shadows, specular reflection, holes, or different layers. Because of these things, they have occlusions, shadow effects. They're basically more complicated than 2D textures. So how can we analyze and synthesize this kind of texture? Our approach is to consider the geometric details explicitly, too. Again, see how can we actually reconstruct these kind of geometric details. So for now, we only consider this kind of height field textures. And so we haven't worked on layer texture yet. That would be a very nice future research topic. See if we have multiple layers of leaves or this kind of thing, whether you can extract these layers. Okay, then you can get very nice synthesis results. So for now, we consider height field type of texture. Say this is one typical image with shadows there. What kind of information we can extract from this shadowed image? Suppose light is from the right. Okay, so since the light from there and these pixels are in shadows, so we can tell the boundary between the illuminated surface and the shadowed surface. The boundary actually is occluder. So because there's occluder, these pixels are in shadow. So it's more clear from this 2D profile. So you can see that's the occluder. And if lighting from there, suppose we know the lighting direction, then it casts a ray like this. So everything below that ray becomes shadowed. So from this, we can get this kind of inequality. Okay, this is based on assumption that we can detect this shadow boundary. And on that, the other side, this pixel actually also, again, on the shadow boundary, but on the other side of the shadow region. At that point, we can accurately estimate the height value. So if we know the height value of this point, because the slope of the line is known. And if you look at some illuminated pixel like this, then obviously none of the lines to its left actually occluded this point. So we can obtain second type of inequality. It says all the points to the left should be lower than the line going through this point. So once we have the shadow boundary and also the shadowed pixels, we can set up some graph. Say that's the occluder, that's some shadowed pixel. So we can set up a graph, set up an edge between these two pixels, and the weight on this edge is the relative height difference. So is this thing, is this quantity there. So that thing is basically the lower bound of the height difference between two pixels. So any pixel here, okay, then this number tells you the difference between that point and some point here on this line. So this point must be lower than that point. So the weight gives a lower bound on height difference. But by introducing this graph, the interesting thing is that, okay, the original light interaction actually has been removed. Okay, we're only concerned about this kind of lower bound on height differences. Then we can move the light source around. At each fixed location, we have such a shadow graph. And if you move the light to a different location, you have a second shadow graph. Then you can simply merge all these graphs together because they have the same set of nodes there. So this is a very compact representation. And you can see it's acyclic if the weights are all positive. Then we can do some further analysis. Say we can run transitive closure on this thing. Then basically propagate all the differences around. If previously there's a path between two pixels, so you have a lower bound on each edge, then you have a edge directly connecting these two pixels in the final graph. Then the weight on that should be set to the maximum weight among all the various paths, because that's the lower bound. So you want to get to the tightest lower bound. So that means you want to get the maximum of all these lower bounds together. That gives you the most accurate estimation of the height difference between these two pixels. Okay. So by doing this kind of graph propagation, we can get all pairwise constraints, height constraints. And after this analysis step, we can extract a special set of the nodes. Most of the nodes should have some incident edge, right? Because they're shadowed. If we move the light source around, they're shadowed in one of the image, then it should have some incident edge. There's some special subset of the nodes that don't have any incident edges. These represent the local peaks. Okay, they don't have they are not shadowed in any of the images. So these are the local peaks. And these are local peaks actually cannot be recovered. The height value of those local peaks cannot be recovered. You have to rely on some other techniques like stereo or some other shape from shading, this kind of technique. But suppose there's only one global peak. Okay, then it's easy. You simply set that global peak to be to some absolute value like 0. Then all the rest of the height of the rest of the pixels can be recovered. If there are more than one local peak, there's some ambiguity there. Okay. So that's some theory behind this shape from shadow problem. So the basic result is that if you move the light source around to a bunch of different locations, you can analyze the shadow graph and get to the upper bound on every pixel, height upper bound. Okay? And there may be some ambiguity on the height of the local peaks. Now, to set up this shadow graph, of course, there's some details like how to perform shadow segmentation. So in our experiment, we basically use thresholding because these kind of images are shot in a special setting, in indoor scene, with curtains pulled down with just one single light source. So it's very easy to detect the shadows by using a threshold. It's not meant for outdoor scenes, natural illumination. And because of noise, there's also maybe cycles. As I mentioned, there shouldn't be any cycles. But if you simply do thresholding, you may have some cycles there. So we need to remove the cycles, extract some optimal acyclic graph. That's some. So we employ some algorithms from polynomial approximation algorithms from graph theory. So as a result, you have this shadow graph, and it requires a dense set of photographs to reconstruct the height value. But our goal is to reconstruct this height from a sparse set of images. And we are basically, up to now, we ignore all the shading information. But there's a bunch of work on shape from shading, photometric stereo, this kind of thing. So we decide to combine these two constraints. Okay, still use shading information, but use shading as local constraints and shadow as some global constraints. Because shadow have absolute height value differences between parallel points. And shading gives you the local constraints on the surface normal. You only need a few local pixels to estimate the surface normal. So that's a local constraint. And we use the shading constraint as some penalty function and the shadow constraint as hard constraints in constraint optimization problem. There's a very huge constraint optimization. So we basically employ some iterative constraint optimization technique. You can borrow some like sequential quadratic programming or bounded least square discounting in MATLAB, but these algorithms run really slow. So we just run a conjugated gradient, but after each step, we reinforce these constraints before then iterative go back to conjugated gradient again. And with multiple iterations, you can actually manage to satisfy all the constraints. So these are some results. This is some input image of a plaster sample. So you can see the shadows in the images. And that's the re-rendered images of the height field. The first image is illuminated from the same lighting direction as this image. And the second one is illuminated from a novel lighting condition. So this is some natural material. I'm not sure what kind of material is this. Looks like a stone or rock. So you can see the real, these are the, for comparison, these are the real images. And that's the synthetic re-render images from the recovered height field. You can see for these images look almost the same. For shadow images, the height field actually is quite accurate, but the difference is in the shading information, because in the real image, the shading has, there's some slight amount of indirect illumination there, so it's not completely dark. But in our rendering, we don't borrow any fancy graphics rendering, so if some point in shadow, we just put it in black. So that's why you see it's darker than those original pixels. But overall, the shadow region looks very close to the original image. That's another interesting material with kind of striped structures. So you can see the lighting, if the lighting changes, you can see these kind of dramatic differences. If the lighting is from the top or bottom, you can, no, from the left or right, you can see these kind of stripes. But from top or bottom, because the lighting direction is almost parallel to the stripes, they disappear. Okay, it looks fairly flat. Our synthetic rendering can reproduce this kind of effect. So that's for explicitly reconstruct geometric details for 3D texture. But that's just represent one of the possibilities. The other thing is bidirectional texture function. That's an image-based technique without any geometry involved. So the concept of BTF was first introduced in this paper by Dana et al. Basically, it's like light field. So given some material with some 3D height relief, you move the camera, okay, move the camera to a dense set of directions, and also move the lighting direction to a dense set of directions. So that's why it's called bidirectional. And for each possible combination of lighting and camera view directions, you take a photograph. So the BTF basically is a collection of photographs. It has an analogy to light field, because if you represent this appearance of this material, you basically has some parametric plane, right? You can place it somewhere close to the surface. And for every pixel on this parametric plane, you have a bunch of pixel values corresponding to different combination of lighting and view. But they don't necessarily correspond to the same point on the height field, right? If the parametric plane is here, then if the camera view is there, actually the color at that point corresponds to the color of that point on the height field. So like in lumograph, if you put the plane close to the real height value, you get more accurate sampling. If the plane is further away, then you get more, actually the sampling rate is going to drop. So this example of BTF for a rough plastic material. So along this direction, the illumination changes, and along the other direction, the view changes. So you can see nicely, this BTF can be nicely represented as 2D array of images. Okay, so that's the starting point of the tensor-based approach I'm going to talk about. Here, the real BTF actually is a 6-dimensional database. Because illumination and the view direction, each of them has two dimensions. Okay, it varies over the hemisphere of the material sample. And the image itself has 2 dimensions. So together it has 6 dimensions. But if we flatten the 2 dimensions in the illumination and the view directions, then we basically can represent it as a 2D array of images. Now, if we want to draw an analogy to a tensor, then tensors are basically multidimensional matrices. The simplest case, the 2D matrix is a tensor, but it's the simplest possible tensor is a 2-dimensional matrix. But you can generalize to high dimensions, like 3D volume is a 3D tensor, 3rd-order tensor. You can even consider 4th or 5th-order tensors. For example, if we had just a collection of a bunch of images together, that's a 3rd-order tensor, right? The image itself is a 2D tensor. It has rows and columns, but the number of images give you the 3rd dimension. So basically, it's a 3-dimensional volume if you put all the images together. But the BTF, as I mentioned, basically it's an array of images. So it's a 4th-order tensor. 2 of the orders represent the rows and columns of the images, and illumination and view represented the other 2 orders. So it's a 4th order. Now, the question is, given this kind of multidimensional matrices, how can we compress and efficiently represent this kind of data? That we need to borrow multilinear algebra, also called the tensor decomposition or approximation. So it's like PCA. We know in PCA, given a matrix of data, like a bunch of columns in the matrix, the one PCA you get decomposed into 3 matrices, right? 2 basis matrices on both sides, and in the middle you have this diagonal matrix. Okay. And a tensor, we can also run a similar decomposition. Now it's high order, so we have multiple basis matrices. Instead of 2, we have, if we consider the image ensemble, it's a 3rd-order tensor, we have 3 basis matrices. And there's also the diagonal matrix is replaced by this core tensor here. Okay. But the difference is that this core tensor is not a diagonal anymore, like PCA. It's more complicated. Now we can try to do approximation and a compression. So I'll talk about the definition of this about multiplication a little bit later. Okay, this is some sort of multiplication between tensor and a matrix. Now, if you want to do compression, right, there must be some redundancy in this representation. So in PCA, we simply discard those bases with small eigenvalues, right? Now here, we can still also try to do that. Say you discard, the least significant columns in these basis matrices. Okay, but that doesn't give you the optimal compression because this is not diagonal anymore. If you simply throw away the last few columns, it's not optimal. So to do optimal approximation, first, we need to figure out how many bases in each matrix we want to keep. Say we want to keep 10 from each one. Then we need to further optimize the bases. Okay, so there's nonlinear optimization involved in there. And a typical technique is called alternating least squares. It's developed actually over the years in applied math. So once you decide the number of bases in each matrix you want to keep, this technique basically optimizes each remaining rows separately. So fix all the other basis matrices, optimize one of the bases, then do this alternatively for each of the basis matrix. Okay. So actually, so we have the paper in this year's graph. The contribution is that actually we observe there's a huge difference in tensor construction. Given some data set, how can you represent this data set so that a more efficient representation or compression can be obtained? There are two possibilities. How to represent image, because we consider a database of images like BTF. So image itself can be considered as a matrix, right? But typically, actually, image is considered as a vector. You basically concatenate all the rows into a huge vector. Then run PCA or tensor texture, like the tensor texture last year also did that. But if you represent image as a huge vector, you just consider the redundancy between different images. You don't exploit the redundancy inside each image because it's a single vector. You don't know how to compress that single vector. If you represent image as a matrix, the rows and the columns of the matrix have spatial redundancy there because we don't consider white noise, right? These images have continuity. If you look at adjacent rows and columns, they are pretty similar, right? That's why image compression has been achieved. They use DCT or other kind of things. Basically, they exploit spatial redundancy. So here we also exploit spatial redundancy by considering image as a 2D subtensor. So as a result, the order of the tensor actually increased by 1. So if for image ensemble, originally PCA could just put it as a 2D matrix, right? Each column is a huge vector. Then you have multiple columns there. But now we represent as a third-order tensor. Okay. A BTF we represent as a fourth-order tensor. But in tensor texture, it's represented as a third-order tensor. So by increasing the order of the tensor, we can exploit more redundancy and achieve more compact compression. The other thing is that when we're dealing with this kind of huge data, typically the amount of data is larger than the memory available on the machine. So out-of-core computation is necessary. So we also developed an out-of-core algorithm to perform this tensor approximation. The idea is very simple. You just decompose the tensor into blocks, okay? And the basis matrix is also into blocks. And it turns out that similar to blockwise matrix multiplication, you can also come up with an algorithm for blockwise tensor multiplication. Okay. Now, let me just briefly introduce this multiplication between tensor and a 2D matrix. The basic idea is that if you want to multiply this tensor with this matrix along this dimension, okay, you have to specify one dimension. Then you retain the other two dimensions, okay? And then you take one column from this tensor and take the dot product between this vector with all the columns in this matrix, okay? Each dot product gives you one number. So as a result, you get a shorter vector out of this multiplication. That changes the dimension, the size of this dimension. So that original tensor becomes this new tensor after this multiplication. And you can see this very similar to matrix multiplication. So we can perform this blockwise. And we only need to load into the memory 2 blocks of the tensors. Here's some basis images for a BTF tensor. So you can see if we represent a BTF as a fourth-order tensor, then each image is a 2D subtensor. Okay. From the basis matrices, we have these basis images. Okay, like PCA, first one looks like the average, right? It's a flattened image, but it's the average of all the images. Then all the other basis images puts more and more details into the images. If you specify some lighting and viewing direction, these lighting and viewing direction specify the weighting coefficients. So you're using the weighting coefficients to combine these basis images together, get you so you can reconstruct some of the original images in the BTF. So these are 3 examples. You can see it has different lighting condition and viewing directions, but that's the Lego BTF. So here's a comparison between on 2 sets of BTF. One is Velvet, the other is Lego. That's the original image. Just the one we just take one of the images from the collection of the images. That's the result from PCA. That's the result from tensor texture. That's our method. So you can see our method can achieve very high quality. All the details are preserved. Okay, all the details in the original text images are preserved. But tensor texture actually, if all these results have the same compression ratio. Okay, same compression ratio. You can see tensor texture actually doesn't have all the details there anymore. And PCA actually performs better than PCA. We know PCA is optimal solution if we consider the data as a 2D matrix. That's the optimal least square solution. But if you consider it as a high order tensor, we can get better results than PCA. That's some error plots. Was again for 2 materials, litching and velvet. The red curves show the errors of our method, and this middle curve shows error of the PCA, and the dashed lines show the error of tensor texture. So you can see our method can achieve a better numerical errors and also better visual quality. Okay, so here's some video. So after compression, we can load this huge data set into memory and perform some fast rendering, map the BTF onto 3D surfaces. So this is a rendering by mapping BTFs onto vase and a sponge. So both the camera direction, view direction and the lighting direction are changing, but the objects are static. So as I mentioned, the objects in a BTF actually is static. Surface is static. But we can generalize BTF to dynamic BTF. Say, if you have a cloth, right? Cloth is deforming, or you have a water surface, it's dynamically evolving. Then how do you represent the appearance of this kind of dynamic evolving surfaces? We can add an extra dimension, the temporal dimension, to the data set. So that gives you a 7-dimensional data set. Okay. For each specific moment in time, you get a 6-dimensional BTF. But if you change the time, you can basically get different BTFs. So we also run an experiment on such a huge data set. Basically, it's a water pool generated from a fluid dynamic simulation. So after simulation, we also retrace the water surface using 9 PCs in 1 week. So it takes a lot of time to retrace all the images. And the resulting data set is this huge data set. The image has, I'm talking about this surface, only water surface. Okay. The rest of the scene is added on later. Just the water surface. The resolution, spatial resolution is 180 by 300. And the view, camera and the illumination directions are 28 each. And there are 240 frames. So it's a dynamic simulation with 240 frames. We compressed this data and re-rendered and mapped onto. So this pool actually is only represented as a planar quadrilateral rectangle. Then we map this dynamic BTF onto this rectangle to create this dynamic appearance of the water. surface. So the sun is moving across the sky, and you can see reflection of the house on the water surface. All these are pre-computed using ray tracing. And you can see the sun is also moving, and you can see these kind of interesting specular highlights. And because it's dynamic, so we can actually run different interpolation in the temporal space. That's why you can do fast forward, slow backward, this kind of thing. You can change the playback rate. And you can even freeze the surface and change the lighting, then make it moving again. Because everything now, the spatial resolution, time, everything is represented as a separate dimension in a data set. We have control of each dimension. Yes?
You said that you captured it or your data set had 28 different camera views.
Yes.
If you try to interpolate between those camera views, does that, how does that look?
Yeah, that gives you. But for different camera views, you need to get dense sampling. But we actually have one example there. I don't have it here.
Do you need to then capture it every single camera view? Can you actually do some sort of interpolation?
Yes, you can get interpolation. But as I said, if the gap is large, it's not going to be very smooth. Okay. You need to, the sampling rate needs to be high along the camera direction.
So what's the compressed size then?
After compression, it's less than 2 gigabytes.
How big is it?
Before it's 30 gigabytes.
If you added more cameras, would that scale linearly, or is that how would that scale? Do you think? If you wanted to, be able to do a 360 view or something like that.
Now that I'm not sure. I haven't done many experiments on that yet. Yeah, so we plan to further crack down the data size. I think 2 gigabytes is still too high. We are still working on it to even achieve higher compression ratio.
In terms of rendering, is there any way to featuring on the texture, on the BTF itself?
Yes. As I mentioned, some smooth interpolation scheme would be good because tensor multilinear model actually doesn't interpret things very smoothly. Like linear interpolation, you can see if the shadow boundary is here, the other frame shadow boundary is there. If you do linear interpolation, you have double boundary. Okay. Multilinear doesn't completely remove this problem.
Okay. If you go far from the surface, and then you have multiple samples of the BTF falling into a single pixel on the screen, so how would you perform quick?
Okay, currently, we do multilinear interpolation. So it's like bilinear interpolation. Now we have 7 dimensions. So it's perform linear interpolation along each dimension. Like in lighter field, it's 4 dimension. You need to do quadrilinear interpolation. Now it's 7 linear interpolations. Okay.
But that's for upsampling, right? How do you downsample?
Downsample.
Yeah. So if you want to sample at a higher resolution, you can do that interpolation. But if you want to downsample, how do you do that? Be the equivalent.
You can still do it. You can still do it, like apply some spline filter along each dimension. Yeah, you can do it separately for each dimension. Yes.
So is there a particular reason to compress to 2 gigabytes? I mean, what does the result look like?
No particular reason. We just want to still achieve high visual quality. Of course, you can correct down to like a few megabytes, but then the image are blurred.
So
okay.
It's very interesting to see the images like this, because something good about those generative models is you can choose the compression rate, like the epidemic model. So it'd be really nice to see for this in a very aggressive compression rate.
Yes, we can do that, but that's not good for graphics anymore. Yes.
How much time does it take to evaluate one frame using the multilinear formula
So at runtime, when you
for this thing, we haven't implemented on GPU yet. It's software. It's 2 seconds per frame. Okay, so we believe it should be possible to achieve real time on GPU implementation. Yeah, basically you perform this linear interpolation along each dimensions and come up with the image. But of course, it's much faster than retracing. Retracing, you need like 40 seconds for each image. So now finally, I think time. Briefly talk about Poisson. So how can we use Poisson equation for texture mixing on surfaces? So let me just briefly recap some of the basics on Poisson-based mesh editing. So the Poisson equation basically, given some vector field, we want to reconstruct a scalar function whose gradient field can best approximate the vector field. Okay. But that's only for one scalar function. Now, if you consider mesh, obviously we need to consider the 3 coordinates as 3 scalar functions. And we basically apply the Poisson equation to each coordinate separately. To achieve editing, we apply local transforms to the triangles so that first rotate the triangles. As a result, the gradient vectors of each triangle also gets transformed. Then the triangle mesh gets broken. So you can solve the Poisson equation to these new vector fields to get a connected mesh again. So that's the idea from last year's graph. So the reason why this Poisson equation is good for this thing, because it can merge different things together. Okay, because it's an optimization, least square optimization. So you can merge different components together, merge broken triangles together into a mesh. And that idea can also be used for texture synthesis from multiple sources and also for other applications. For example, if you merge different meshes, you can specify partial meshes, right? And here on the teapot, you cut a hole. Then you specify some simple correspondence on the vertices, the boundary vertices. Then the Poisson equation can merge these two things together without any obvious seam. Obvious seam among them, okay? Because it takes the gradient and reconstruct a global scalar function using this gradients, local gradients. So it globally adjusts each partial mesh so that they can match each other, be more compatible with each other. And this idea can be generalized to texture mixing, right? So typically, we only synthesize texture from one example, but that's really limited, right? One small example gives you very limited variability. But if we want to mix different texture together, there's some previous work on texture mixing. But if you consider textures with this kind of thing, with very different illumination color, okay, even though you know these are very similar, these are all leaves, okay, but they have very different illumination in this kind of thing. So if you synthesize them together on the mesh, you can see this kind of problem. They have very high contrast because they're from different sources. So the problem is we want to use Poisson equation to merge these different textures to get a more consistent mapping. So on the right, that's the result after this merging. This is the result from local blending. So on the boundary, you can perform some local blending, but still the contrast is still there. And after this global, so we take the gradient or Laplacian of this texture, then resolve the whole texture. Okay, we throw away the original texture color just to keep the differential properties, and resolve the color again. That'll give you more consistent color. So this is another example on a camel mesh. This is a radish and a leaf texture. So we figured the leaves in the radish seems too few, so we add more leaves, and by mixing these two textures together and solve it. so that they blend with each other naturally. Here's another example. So this flower example is frequently used in texture synthesis. You can see there's too many flowers, and the green grass actually is a tiny bit of green grass. If you see inside this texture on a bunny model, it's basically flower everywhere. It's not very interesting. Okay, very boring results with red flowers everywhere. So we want to make it more interesting by adding leaves, green and the yellow leaves together to create this result. Okay, so here actually this is local, this is global. It's hard to tell whether global is better because the local reconstruction gives you more rich color. The global things make color more consistent, but it removes some of the high contrast present in original textures. Which one do you find more interesting? Hard to tell in this case, right? Okay. So we can also perform some fluid simulation on surfaces. In fluid dynamics, we typically need to solve this kind of differential equations. And in this equation, the very important step is to make the fluid incompressible. Okay, because of the incompressibility, the fluid moves like fluid. Okay, interesting motion. So to enforce this incompressibility, there's a projection step in the algorithm. Okay, that basically needs to solve the Poisson equation. So you get some intermediate velocity field and set up Poisson equation like this and solve the pressure. The pressure is basically the Poisson equation for pressure. Once we get to the pressure field, then we can subtract the velocity, the gradient of the pressure from some intermediate velocity field to get a divergence-free velocity field, which is what we need. So here's a demo. So you can see on the surface, by enforcing the incompressibility by solving this Poisson equation, we have very nice fluid motion on the mesh. All these turbulence kind of thing, rotational motion, wouldn't be there if you don't solve the Poisson equation. Okay, we also did it for the bunny. Okay, so do I still have a few more minutes?
I think we have room for 12. It's
Okay.
really up to you.
Okay.
How much time do you want to leave
Okay.
for questions?
Let me just show some additional. Let me just briefly show another project that's unrelated to texture at all. It's just related to fluid animation. So we did some project on controllable animation. Like Zoran Popovic, he did a similar thing at UW. So we want to control the motion of fluid so that it follows some underlying guiding sequence. Okay, suppose you are given some guiding sequence like this. Starting from smoke, you want the smoke to become some shape, interesting object. Okay, so we create this transition using shape interpolation. Then, given this shape, we want to create some smoke sequence like this. It follows the shape interpolation sequence, but it has the smoke appearance there. It has smoke appearance and the dynamics there. Let me show the animation. And a wind can blow away a part of the object, can still grows back. So you can see there's difference between dissolving and our controllable smoke. The shape doesn't simply emerge from a cloud of smoke. We have control over the smoke boundary. So the smoke shape really evolves into this shape. Okay, so that's all. I would like to thank collaborators and the funding agencies. Thank you. I can take some questions. Yes.
A question on the compression stuff.
Okay.
So you mentioned that you use PCA because you sort of put all the pixels in one big vector, so you don't take advantage of the coherence between the pixels.
Yeah.
So what if you just do a DCT for each image before you do PCA? So you compress each image first with those traditional methods, right? Then you get a vector.
Then you get to the DCT coefficients.
That's right. Then you PCA on the DCT coefficients, right?
Okay.
So then you take advantage of the coherence with pixels.
Yeah, we haven't compared with DCT type of thing. Okay. Yeah, that would be a good thing to pursue actually, because DCT, which stage you want to consider DCT? You can perform DCT first, compress the coefficients, or perform tensor first, then DCT the tensor coefficients. Yeah. I'm sure you can get better compression ratio by doing that. But now we are only doing tensor thing.
No more questions?
Okay. Thank you.